to our final presentation. Our final year project is entitled Application of Data Mining Techniques and Time Series Forecasting in Predicting Electricity Consumption, a case study of Guyana. These are my group members and our respective supervisors. We will now recap the key ideas or the essence behind this project for the benefit of those who may not be halfway with it. GPL is a major supplier of electricity. However, something appears to be lacking in the resource allocation and management process. According to multiple news articles, power outages have been a never-ending problem in Guyana. One East Coast resident reported by a 2019 iNews article indicated that this issue can occur 10 times per day or sometimes as much as 20 times in a single day. So what is GPL doing about this? In 2014, they would have rolled out the AMI meter installation program to gather more data on consumption. However, to date, the data being collected by these meters has not been harnessed adequately using data mining and time series forecasting to inform their decision-making processes. The current measures for dealing with issues of power outages include the SIFI, or System Average Interruption Frequency Index, which measures the frequency of power outages, and the SIDI, or the System Average Interruption Duration Index, which measures the average amount of time power outages. Both metrics are evaluated on a yearly basis to see where improvements have been made. However, even in 2018, these values were still high in comparison to what they would have estimated. As seen in the table here, the actual SIFI value had surpassed the annual targeted value in the third quarter of 2018.
Okay. Development of an e-selection framework
by already 13 units, and the SIDI's case by 6.9 hours. It is obvious that the data being processed by the AMI meters is being underutilized, and a new solution may hold the key to changing these values into favorable ones. We propose that utilizing the power of data mining and time series forecasting in conjunction with the data from the AMI meters can be used to harness a more favorable outcome. Data mining is the analysis and summarization of data in novel ways, while the aim of time series forecasting is to use past or historical data to predict future values. These activities can be invaluable assets to GPL's decision-making process. Their techniques would be leveraged to produce predictions of future electricity consumption by different locations. The predictions can then be used as informative guidance in resource allocation and operational decisions to avoid the persistent issues of untimely power outages. Several studies have been conducted showing the effectiveness of using data mining and time series forecasting to garner insight into future values. And the graph seen here is an example of one such study. Yasmin and Sharif successfully conducted this study on a large dataset using time series models to forecast electricity consumption in Pakistan. Our intention was to leverage the data processed by GPL's AMI meters to develop the best fitted forecasting model. The diagram displayed here depicts conceptually the entire process undertaken to arrive at the ultimate outcome. This is deriving a best fitted model. In order to realize the proposed solution, we needed to investigate the use of data mining and time series forecasting techniques in constructing predictive models for electricity consumption in selective areas of Guyana. In order to achieve the aim, there were three objectives in this study. The first was to construct predictive models using the necessary techniques. Secondly, determine the best fitted or most accurate model for predicting customer electricity consumption patterns. And last but not least, to use the results of the best fitted model to aid business intelligence. Now that we know what we are working towards, let's talk about the dataset. A novel contribution of our study lies in our use of a relatively small dataset, consisting of just 5 years' worth of monthly time series data, with only 60 records. Other studies undertaken in similar areas, such as the one done in Pakistan, would have used 20 years worth of data with over 1,000 records. We will now move to discuss our evaluation metrics.
To determine the best fitted model, we used evaluation metrics to obtain the model's comparative performance values, residual diagnostics to analyze their residuals, and also attempted K4 cross-validation to test for additional performances. With the evaluation metrics, they were evaluated based on their mean square error values, MSE, which measured the average square difference between their estimated and actual values, their root mean square error values, RMSE, that give a measurement of their standardized errors, their mean absolute error values, MAE, a metric that provided the average magnitude of the errors in their prediction, and also their mean absolute percentage error values, MAPE, that further measured the overall size of their errors in percentage. Point to note is that MAE, unlike RMSE, does not emphasize the presence of large errors. All techniques were used with the exception of K4 cross-validation. In the initial stages of proposing these evaluation techniques for the study, K4 cross-validation looked very viable due to the magnitude of the pure data set. But upon further transformation of the data set to adequately address the aim and by extension the objectives of this study, the data set became smaller and K4 cross-validation was no longer a viable option since it required a moderately large data set to be used efficiently. Now let's talk about the results of our evaluation for the different models. Seasonal autoregressive integrative moving average, also known as SARIMA, is a univariate time series forecasting method. What we found was that out of all the resulting models, this particular model exhibited the lowest values across all evaluation metrics for the different data sets as depicted in the diagram. The lower the values for these metrics, the more accurate the said model is, and hence we concluded that SARIMA was the best fitted model across the different data sets based on these results. Additionally, residual diagnostics conducted on the models revealed that the SARIMA models, while they did not account for the total variability in electricity consumption data, did a better job at explaining the variation when compared to the other models. The residuals, also known as the error or unexplained values, were plotted against the fitted values to check for randomness and noticeable patterns in their distribution around the zero line. The diagrams here highlight a portion of the diagnostic residual performances for the SARIMA models across the different groups. The model derived from the general monthly consumption group displayed a less distinct pattern and a fairly normal distribution of its data points when compared to the low monthly group, where a noticeable up and down pattern was evident along with most of the data points residing above the line. An ideal residual plot should result in the data points being evenly distributed around the line and no systematic or clear pattern should be present. Against this backdrop, the model from the general consumption group produced the best results when the residuals were analyzed. Even further, the residual diagnoses of the SARIMA model obtained from the medium and high monthly consumption groups furnished no better results than the previous model from the general monthly group. However, while the results from the high consumption group closely mirror that of this model, the one from the medium group delivered the worst results. As seen in the diagram on the left, there was an overall declining linear pattern across the residual. The bulk of it was concentrated above the zero line, and there was a distinct presence of an outlier. This showed clearly that there was a large portion of the electricity consumption data unaccounted for by this model.
We will now explore some key findings that arose during the course of this study. Surima was found to be the best fitted model in all cases, that is, the general, low, medium, and high consumption datasets. This is supported by the evaluation metrics which showed favorable results. The dataset was relatively small, being only for 5 years, and due to this, predicting on a yearly time frame would not be possible, since the training set would literally comprise of 3 observations, and no model can learn from just 3 observations. Surima relies on the dataset exhibiting certain features such as stationarity and having a seasonal component. Techniques such as log transform and differencing were used to make the data stationary, but the results obtained in the second year of prediction were not as favorable as seen in the graph. The patterns occurring in the first year being predicted were evident in the training set, and hence prediction was moderately accurate. However, in the case of the second year, these patterns were absent in the training set and hence could not be adequately accounted for. The erratic movements seen in 2018 of the observed data are termed as highly volatile. Volatility can be accurately accounted for with models such as ARCH and GARCH. However, these models require that the data exhibit autocorrelation, which it did not. In addressing the objectives and overall aim of this study, we have discerned the following conclusions. So the million-dollar question now is, did we cover the objectives? To answer each objective, we present these conclusions. The ARIMA class of models can be used on small datasets with a fair degree of accuracy. However, there is a limitation on how small a dataset can be when using this class of models. This ARIMA model is especially useful when handling data on a seasonal basis. Due to the nature of the data transformation process undertaken, GPL can use the filtered source datasets to gain meaningful business intelligence to make informed decisions. These are a few of the limitations we identified. The state of the original dataset was not expected, and this changed the path of the project. Choices of modeling techniques were based on explored literature. Nearly 25% of the data was lost due to either being absent or faulty while cleaning the dataset. There are unknown factors that may affect consumption. In closing, we will now address some alternate routes that could have been explored in an attempt to improve the final results. A future undertaking of this project should involve a closer relation with the company data and better formatted dataset. The data preprocessing methods that were employed were used for convenience given the shape of the data and the end result that was anticipated. The use of different software and techniques can prove otherwise. A few variables in the initial dataset were not considered in the interest of the techniques employed. However, it is believed that these additional variables may have an impact on the study. The techniques employed were chosen after careful consideration, but it is acknowledged that there are other techniques that can yield more conducive results. These are a few of our references. Thank you for listening to our presentation.